The Australian Bureau of Statistics tells us that more children die of injury than from cancer, asthma and infectious diseases combined. Injuries in playgrounds usually occur when a child falls from play equipment onto a hard surface. Professional engineers have performed a role in establishing playground safety standards to reduce the severity of injuries due to falls, and continue to have a role in testing playground surfaces using tests like the one shown in this video.
Welcome to the Dynamics Lab. My name is David Eager and I'm one of the professors here at UTS Engineering, and to help me is the laboratory manager Chris Chapman. We're going to demonstrate today the usage of some equipment that we've developed here at the university for measuring the performance of playground surfacing. You've probably all been to a playground, played in them yourselves, and noticed that there's rubber surfacing, impact attenuating surfacing, there'll be bark, there'll be sand. And you may have wondered, is there an Australian standard for the performance of that surface? Well, yes, there is. AS/NZS 4422 sets out the performance characteristics of playground surfaces. They are pass-fail. We have a 1000 HIC, head injury criteria, and we have a 200 G max criteria. We use an instrumented head form. In this case, it's a 4.6 kg head form. We also have a 5 kg J shape head form. Inside the head form, we have 3 accelerometers. They're orientated orthogonally. We've got Z, X and Y. And if you look closely inside the head form, there's a little blue rectangle, and that's an accelerometer. They're quite expensive. They're what, about 1,500?
Yeah, about 1,500
each. So quite a lot of money, but they're fairly robust. And they're basically strain gauges. They measure the strain when an acceleration or a negative acceleration occurs, and we get an output on the screen here. It's really a voltage. So when they're strained, we produce a voltage, and the voltage travels along this umbilical cord into a data acquisition system in the USB port of the computer. We sample at 25,000 samples per second for each channel, so every 40 microseconds. Before we use the system, we do some calibration and we just make sure it's working. And one of the simple things that we do is we do what's called a 1G inversion. And if you look at the screen here, the Z is the orange sample, and if I turn this over, you can see that line moves. We can also demonstrate the X and the Y, and Chris will do that now by the Z.
That's tapping in the Z direction, vertically up. So we get something on the Z, but not much on the X and Y. We tap horizontally, we pick up more on the X or the Y.
So the blue and the green. Okay, so I said there's 3 accelerometers. We do a vector sum of the accelerometers, so that's x squared plus y squared plus z squared, and we get the square root of them, and that's what we call the G max, the maximum G, and on the screen that's the yellow line. Let's do a drop, Chris, and demonstrate a drop for them.
armed and dropping.
Notice how high it bounced. So we dropped from 1.5 metres and you saw it bounce, and the software worked out the bounce at 628 millimetres. It worked out the fall height at 1481. It did that using equations of motion. So the previous graph was a time along the x-axis and acceleration, or g's, on the y-axis. What we have here is the area under the curve, or the velocity, and here we have the displacement, which is the velocity is the first derivative with respect to time. The acceleration is the second derivative with respect to time, and the one down here, which you don't have to be too concerned about, is the third derivative with respect to time, which we call jerk. There are a number of ways that you can calculate the solutions to this. You can use the energy method, you can use the equations of motion. I'll demonstrate the energy method, and then I'll hand over to Chris, who will talk to you about the equations of motion. So I told you the head form is 4.6 kgs. It's 1.5 metres from the ground, and you know that the potential energy is mgh. Mass times the gravitational constant, 9.81 metres per second squared, and the height, 1.5 metres. So before release, we have maximum P, or potential energy. When we release, we gradually reduce the potential energy and increase the kinetic energy. And as we get closer and closer to the ground, and just prior to impact, we have maximum kinetic energy and zero potential energy. So maximum kinetic energy is a half mv squared. So we know how many joules we have, mgh, and that should equal a half mv squared just prior to impact. When we impact, we do work on the surface, and the work is the force times the distance, and the distance is the penetration into the sample. You probably didn't see it, but we've got a video which we will demonstrate later, where the displacement was, in this case, approximately 20 millimetres. So it went into the sample 20 millimetres, as shown on the screen here. Our eyes don't pick it up, but we know from high-speed film and also from the mathematics that it did penetrate that far. So, Chris, would you like to describe the other method, the equations of motion?
Sure. Okay. So, Dave's talking about how to calculate what's going on using the energy method. Well, I'm going to show you how we can do the same using the equations of motion. For this, we divide the whole sequence up into 4 stages. The first stage is prior to release, where the head form is hanging from our release mount, and its distance off the surface is fixed at 1.5 metres. So the distance is constant. Velocity is also constant because it's just hanging there, not doing anything. Same for acceleration. Throughout this analysis, for displacement, velocity and acceleration, the convention is positive is upwards, negative is downwards. Now, during the free fall, our distance obviously is varying throughout this part of the stage, as is velocity. Velocity is going from 0 up to the impact velocity. And the acceleration is constant, minus 9.81 metres per second squared. And during this stage, because we have constant acceleration, we can use the equations of motion that assume constant acceleration. For the third stage, that's actually during the impact stage, lots of things are changing. This is obviously varying. When d is equal to 0, the head form is just touching the surface, and during this stage, the head form will penetrate into the surface. And if we graph the displacement, it will look something like this. Start off above 0 before impact, go through 0 and go negative to some minimum, and come back up again. Also during this stage, the velocity is varying, and the acceleration is the acceleration pulse we got as displayed up on the computer there. So the acceleration starts from 0g and then goes up to maximum and comes back down again. Because acceleration is varying, that's what gives us varying velocity and varying displacement. The convention we use for the beginning and the end time marks for the impact T start and T end. During this sequence, if the data we get is acceleration, if we integrate that acceleration, we get our velocity. So the velocity is the integral, acceleration, T, from T start to T end. And of course, whenever we do any integral, we always get an integration constant. In this case, we can solve for that because we know that at the beginning of the integration, our starting velocity is our impact velocity. Our impact velocity we can calculate from the drop line. So the graph velocity starts off negative, the impact. It goes up through 0 and then becomes positive with V bounce. V bounce is the velocity that the head form emerges from the rubber just as it loses contact. Similarly for displacement, we can integrate velocity to get displacement. So displacement, integral of velocity from T start to T end. And again, we have an integration constant we need to address. In this case, we know that the displacement is 0 just at the T start, at the beginning of the start of contact with the head form. Now during the rebound is somewhat similar to stage 2, the free fall. During rebound, the head form is travelling up, so our distance is varying, our velocity is varying. Our velocity is going from V bounce at the beginning up to 0 at apogee or maximum height, and then our velocity goes negative as it falls back down. During this time, it's a bit counterintuitive, the acceleration is constant, and that's minus 9.81 meters per second squared, which when you think about it, those three, acceleration, displacement, velocity, acceleration, those parameters are the same as what's happening here in stage 2. The only difference is that we start off with the velocity going up. And so because of that, the equations of motion for this stage are the same as per stage 2. Knowing that at maximum height velocity is equal to 0, we can actually calculate the bounce height that it gets to. And that's how we use the equations of motion to calculate what's happening at various stages.
In children's playgrounds, we have two pass-fail criteria. We have 1,000 head injury criteria, unitless number, and we also have the 200G. So if a drop exceeds 200G or it exceeds 1,000 HIC, it's a fail. What is it? How do we get these numbers and where do they come from? Well, there's been a lot of research done in the motor vehicle industry, particularly in America, and what they've got are probability curves, and they've got a probability, well, they've done a bunch of experiments on humans when they were allowed to do them. They've done them on hogs or pigs, and they've done them on chimpanzees, and they've also done them on cadavers, like they've broken skulls. And they've plotted data against acceleration, and they've found that 1,000 HIC or 200G, you've got a 3% chance of death if you're white Caucasian male and you get a frontal lobe impact. So that's our pass-fail criteria. It doesn't prevent children from having accidents, but what it's set out to do is prevent children from dying in playgrounds, in Australian playgrounds. And since the Australian standard NZS 4422 has been published, we've had no death through falling in a playground. What we have had is an increase in long bone injuries, and we at UTS have done considerable research on that, and we've come to the conclusion that the introduction of rubber, which gives you bounce, has been one of the contributing factors in the increase in long bone injuries around Australia. It's important that we get a clean release, and we've designed an electromagnet. It's a permanent magnet that releases the head form very cleanly, and we drive it open with batteries. So when you hear that buzz, it's releasing the head form, and it's releasing it, and we drive the field away. It has a safety factor of 3. Head form, we assume, is 5 kgs, in this case it's 4.6, and the magnet can hold 15 kgs. I'm now going to demonstrate a fall from 1.5 metres. We're on.
Okay, and dropping.
Notice the height that it bounced to. In this case, the software calculated a bounce height of 547 millimetres and a fall height of 1440 millimetres. Now, I said that we know when it releases, and we also know when it contacts. So we have a time over which the fall happens, and from that time we can calculate the height using equations of motion. So why don't we do a demonstration, Chris?
Okie dokie. I'll arm it. Computer's armed, it's now ready for the impact data. I'm releasing now.
Notice how high it bounced.
That bounced to about 660 millimetres.
How did it do that, Chris?
Well, obviously some of the energy in the rubber was returned to the head form. Some energy was absorbed as heat, some was returned to the head form, which pushed it back up again, just like a spring.
But how did the computer know it was 663 millimetres?
Bit of data processing, bit of number crunching. We, under this acceleration curve, we integrate that to give us the change in velocity. So our initial velocity is the impact velocity, which we can calculate from the drop height. The area under the curve of acceleration is the change in velocity. The initial velocity is negative. Negative is down in this instance. We go through 0 to positive velocity. And then we do the same for this curve to get displacement. Integrate under the velocity curve to give us change in displacement. And we say 0 displacement in this case is the start of the impact.
We're going to do a demonstration on the parquetry floor here to do a bit of a reality check or a calibration of how good the mats are in attenuating the fall. So Chris, I'll just arm it, and if you could drop, so you're armed.
And dropping.
Wow. So what we've got here, from that very small height, we've got 300 Gs. So recalling we were dropping from 1.5 metres onto the rubber, we were getting way less than 200. We've only dropped a small distance onto parquetry floor, and we've got a G max of 300. Now this is really, really bad, and we know that the injury pattern is changing in households around Australia. Construction is happening now on slabs, so we're building McMansions on concrete slabs, and we might put parquetry, we might put some cork material, or we might put carpet on that. But what we do know in the accident and emergency departments of hospitals and children's hospitals all around Australia, is that we're getting more fall-related injuries from children in households.